Hello, everyone. Okay, today we are going to continue with solving some problems about fields and vector spaces. Remember that the due date for your homework is 17th of this month. So because you still have not handed your homework, we are going to just solve some problems. Probably from next week or the week after that, I would also solve your homework in the recitation too. Okay, before I start, is there any question?
Could I ask a question?
Yes, sure.
So I took a look at Axler textbook.
Mm-hmm.
Do you have any you know of any better textbooks for linear algebra? I think that Axler is not going in depth as the professor is.
Well, I think for now it's better to stick to your textbook. After the first midterm that you decide either to stay in 310 or to move to 315, then based on who is your professor and what course exactly you're following, that would be possible to choose a better reference. Okay, does that make sense?
Yeah.
Good. Okay. So if there isn't any other question, let's start. Okay, I would start with a problem which looks very easy. It is very easy, but it's nice to know what we really mean by a proof. So suppose F is a field and V is a vector space. Okay, and also suppose, say, A is an element of this field and V is an element of this vector space. Okay. I want to prove if A as an element of the field times V as a vector is 0, it implies either A is 0 or the vector V is 0. Okay, this looks very simple, right? I just want to say, first of all, what does it mean to prove it? So we have a definition for a field and we have a definition for vector space. You remember, right? When we want to prove something, we should only use those axioms we had for definition of a field and a vector space and nothing else. That's one thing. So we should only follow those specific rules. And the other thing is that, well, it's not hard. I guess you also know it. But there is a difference here between the first 0 and the second 0. The first 0 is the 0 in F, the 0 of the field, and the second 0 is the 0 of the vector space. So they are different zeros, although I'm using the same notation for both of them, but they are actually different elements. Okay, so you might want to think about the proof for maybe a minute or two, and then I would prove it, okay? Whenever you have the answer, you can just unmute yourself and share your answer with the rest of us. Okay, let me start. Does anyone have the answer?
Can you start with scalar multiplication to express that as a list of v1, v2, v3 equal to 0, 0, 0?
Are you assuming the vector space V is, for example, Rn or f to the n?
Probably f to the n, so that it's the most general case.
Okay. Okay, I would write down the proof and then I will come back to your answer. It's almost correct, but not always. Okay. So, so we have A times V is equal to 0. So look at A. A is an element of the field. Okay. We know something about the elements of the field. So suppose just it's kind of, well, think about the definition of the field. Almost every element of the field has multiplicative inverse, but not exactly every element. Do you remember which elements of a field they have multiplicative inverse? You can just say it.
Every element besides for 0?
That is correct. Every non-zero element in the field has multiplicative inverse, just like R, right? Every non-zero number, you can, for any non-zero number A, you can consider what we should, the number which we usually should with 1 over A, or A inverse. So if A is not 0, so if A is an element in F minus 0. Also, this notation is usually, it means minus, but for sets. Usually we call it set minus. Okay. So suppose, well, I want to show either A is 0 or V is 0, right? So either A is 0 or A is not 0. That's trivial. Anything either is 0 or it's not 0. If it's not 0, if A is not 0, I want to show in that case, I want to show that in that case, the vector V is 0. Okay, so let's go back to the assumption. We know A times V is 0, and we know A is non-zero. And because any non-zero element in a field has multiplicative inverse, it means we have 1 over A, or A inverse, right, in the field. Now look at this equation, the equation with red star. I can multiply both sides of the equation with a number. So I can multiply both sides of this equation, AV equals 0, by A inverse. Okay. So on the right-hand side, we have A inverse times 0. What is that? What is the multiplication of A inverse and 0? It's 0, right? So A inverse times 0 is 0. That looks trivial. That looks trivial. Anything times 0 should be 0. That seems to be the case. But we still have not proved that as a fact. We know that's correct for real numbers. We know any real number times 0 is 0. But now we are not in the set of real numbers. If we want to use this fact that A inverse times 0 is 0, we should prove that. So it is something we should prove. We should prove this thing. We should prove. Okay. So let's first prove that, and then I would continue with the proof. So first, we need a lemma. So let's call this lemma 1. We need to prove, rather than A inverse, I want to say any number. So for any number, for any element, for anything, let's say B. For anything in the field, I want to say B times 0 is 0. That's lemma number 1. Before proving that, let's assume it is correct for a second. Let's see what's going to happen. If I assume this is correct, it means then A inverse times AV is equal to 0, right? So it means A inverse times A times V is equal to 0. Here we have parentheses to mention that first I'm multiplying A by V, and then I'm multiplying the result by A inverse. But remember, we had a property which was telling us, so we had a property, it was part of definition of a vector space, which was telling us, say, B times C times the vector V, when B and C are two elements in vector field, in the vector, in the field, and V is an element in the vector space, this multiplication is actually equal to BC times V. This was one of the properties of any vector space. So here, using this property, we understand what we have here, A inverse times AV is equal to A inverse times A. First, we multiply these two elements, and then we multiply the result by the vector V. So this is one of the properties, one of the parts of definition of a vector space. Now, what is A inverse times A? By definition, this is 1. So A inverse times A, by definition, is 1. And 1 times any vector V is equal to V. This was another axiom, another part of the definition of a vector space. It means this A inverse times A times V is actually equal to V. On the other hand, the same quantity, A inverse times A times V, is equal to 0. So if this thing is equal to V, and at the same time it is equal to 0, then V has to be 0. So going back to the beginning of the proof, I said either A is 0 or not 0. And then we showed if A is not 0, then V has to be 0. So if we want to wrap up what we did here, it means either A is 0 or V is 0. There is just one part of the proof which is not rigorous yet, and that's this part, lemma 1. We used the fact that any element in the field times 0 is 0. I should say this 0 here is the vector 0. Vector 0. So it reminds me, maybe in order to stop prevent any confusion, I use slightly different notation. So we have a 0 in vector space, and we have a 0 in our field. Maybe one good way to kind of recognize these two elements and not confuse them is to use an arrow above this 0 in the vector space. Okay, so when I write 0 with an arrow above it, I mean the vector 0. So what I want to prove is that for any element B in the field times vector 0, we would get 0. Okay, so that's lemma. And that's pretty straightforward. Why? So let me write down the proof of this lemma too. Look at this vector 0 plus the same vector 0. The result would be still the vector 0, right? Now multiply both sides by this number, by this element in the field B. So what we would get is that B times 0 plus 0 is equal to 0. Therefore, B times 0 on the right-hand side. Now, we had distribution of multiplication over sum. So the left-hand side is equal to B times 0 plus B times 0 is equal to B times 0. Another property of vector spaces is that any vector has additive inverse. So we can add minus B times 0 to both sides. Okay, on the left-hand side, these two would cancel. On the right-hand side, these two would cancel. On the left-hand side, we would have B times 0. On the right-hand side, we would have 0. So any number B. Usually when I say number, I mean an element in the field. Okay, any element in the field times the vector 0 is equal to 0. And this 0 on the right hand side again is a vector. So I would use an arrow to like prevent any confusion. Okay, is there any question here?
So in the lemma, there should be an arrow above at 0 on the right side, or?
Yeah, that is correct. Thank you. Yeah. So yeah, because multiplication, that's a good point. So always multiplication of an element in the field with a vector, the result of that multiplication is another vector. Yeah. So here we have an element in the field B and the vector 0. The multiplication would still be 0. So okay. So as you can see here, the kind of the statement seemed kind of trivial, right? You have multiplication of two things, the result is 0, so one of them should be 0. But as you can see, the rigorous proof has some steps. So for example, in the exam or in the homework, when you are solving these things, you should pay attention at each step, which property of the definition of a field or a vector space you're using. Okay.
Is it enough to just explicitly have in parentheses which axiom you're using, or should you also write because of so-and-so axiom for the homework?
Can you repeat that? You said we should write which axiom we are using or what?
Yeah, should we also write out explicitly the axiom itself as we go through the steps for the homework, or is it enough to just have it in parentheses so that it's clear?
Well, I'm not sure if all the graders, they expect you the same thing or not, but I think it would be very nice both for yourselves when you're learning it to write down which part of the definition you're using, and also for the person who is grading to make sure you know what you're doing. That would be very good, yeah. So let me mention, let me address another solution that was, I heard someone suggested another solution. So we know when we have our field is the set of real numbers with its standard field structure, our vector spaces, as much as we know, they usually look like something like this, Rn, right? So also for usual field F, the vector space, you might guess it would look like Fn. You might say any vector space over field F would look like Fn for some n. That's not exactly correct. So the reason that's not always true is that, well, there are different reasons. Let me just mention the most understandable one. That's the fact that all vector spaces are not so-called finite dimensional. So here, for example, when we write V is equal or at least isomorphic to Rn, it means the vector space in some sense is n-dimensional. So we know R is one-dimensional, R2 is two-dimensional, R3 is three-dimensional, and etc. Rn is n-dimensional. But it's not correct that all vector spaces are finite dimensional. We have infinite dimensional vector spaces. And there is no usually best way to write them as, say, R to some power, some infinite power. Okay, so if we have a finite dimensional vector space, there is a way to write it. If we have a finite dimensional vector space over R, there is a way to write it as R to the n. But in many cases, we would see one example today of a vector space which is not finite dimensional. And the proof we just gave, it works even if the vector space V, which we were talking about, was infinite dimensional. Okay, that is quite important to understand. Vector spaces are not exactly what we have always in mind, like R2 and R3. They might even be infinite dimensional. Okay, so let's focus on another aspect of vector spaces, and that's subspaces. Subspaces of vector spaces. Okay, have you seen this concept before in the class?
I
think it was.
Yeah, okay. So, okay, I would just review it very fast if in the case that you have forgotten. So suppose we have a vector spaces. For simplicity, let's start with R2, okay? By a subspace of this space, I mean something like this. So if you look at this red line, it is still a vector space itself. It's just a line. It's a vector space, right? And it's a vector space inside another vector space. That's kind of what we would have in mind when we talk about subspaces. Or if you think about R3, it's a vector space. If you look at a plane which passes through the origin, suppose this is another plane which passes through origin, this plane goes to infinity from each direction. It's like a copy of R2 inside R3. It's a subspace. It's a two-dimensional subspace. Or think about a line which passes through the origin. It's another subspace. Okay, so we say when we have a vector space V, we say W inside V is a vector subspace if, well, first of all, if it has 0, the vector 0 is inside this subspace too. So as you can see, I mentioned both of these subspaces, they should pass through the origin. They have the vector 0 inside them. The second thing is that if we have two vectors A and B, these two are vectors inside this W, their sum should also be inside that. So for example, if I take one vector here in this plane and another vector here in this plane, their sum would still be inside this plane. And the third property is that if I take a vector inside this subspace, minus that vector should still be inside that subspace. So if, for example, I take an element here, A inside this line, minus A would still be inside this line. Okay. So this is the definition of a vector subspace. Let's look at some examples.
I have a quick question.
Yes, sure.
About the previous slide. So you said all of these subspaces are going to infinity, right?
Yeah.
So the R3 and then the line is in R1 and then the plane is in R2, right?
Yeah, they are extended to infinity in every direction.
Okay, I just wanted to double check and make sure like one of them wasn't like restricted.
Yeah, yeah. So that is correct. Actually, something which I have not written here, maybe I should write that more explicitly. If any vector is here, I mentioned that V itself should be a vector space. So if any A is inside this space, for any element R in the field, R times this vector should also be here. So for example, if I have this vector here, A, for any element in our field, say here we are working with real numbers in this example. So for example, number 2 is an element in the field. So 2 times A should also be here. 3 times A should also be here, and etc. So it kind of goes to infinity in the case of R. So these segments I have here is just to mention, I mean a plane. It doesn't mean it's limited here. they really go to infinity in every direction. Okay. So let's consider another example of a vector space. Consider, say here, our field is just the real field, R, and define V to be the set of n by n matrices. We usually show it with this notation, M, n by n matrices over R. It means the set of all n by n matrices. So V is actually equal to, with components coming from real numbers. So the elements inside this space is the set of matrices, which they have n rows, they have n columns, and each element in this matrix is a real number. So components are an element of R. Is everyone familiar with the definition of a matrix? Should I review that?
I have like a basic understanding of it, but like if it has something to do with proofs, it'll probably be nice to like review.
Yeah. Okay. So here, okay, as we go forward, at each step, I would remind you the related property of the matrices which we need to know. As the first step, by a matrix, we just mean a table of numbers. So for example, an example of a 2 by 2 matrix is just a table which has 2 rows and 2 columns. So it looks like this. It has 2 rows and 2 columns. And you can just write down any number you want there. So for example, say 0, 1, -3, 4. It's just example of 2 by 2 matrix. Or for example, another example, say 3 by 2 matrix, it would have 3 rows. And the first number here, okay, I should say that. The first number here is the number of rows. So we have 3, and the second one is the number of columns. So there would be 2 columns. And then you just fill that with numbers. Say 1, 0, 1, -1, 2, 3, 4. So it's just a table of numbers, right? At this point, that's just it for us. Now, moreover, when we have 2 matrix, say we have 2 by 2 matrix, say one of them is 2, 3, 1, 0. This is one matrix. I have another matrix here, say -1, 4, 6, 2. We can add these 2 matrices. So we have the notion of sum. And this means we should just add them component by component. So here, this component here, we have 2. The corresponding component in the second matrix is -1. We should just add these two. 2 plus -1 is 1. So here, in the 1, 1 component of the final matrix, I would just write down 1. I have 3 in the corresponding component. I have 4. Their sum is 7. Here I have 1. Here I have 6. Their sum again is 7. Here I have 0. Here I have 2. Their sum is 2. So I have this notion of sum of matrices. It doesn't matter for 2 by 2, for 3 by 2, always it's similar. The point that matters is that when we are adding 2 matrices, their so-called dimensions, the number of rows, number of columns, they should be the same. By that I mean we can have 2 3 by 2 matrices and we can add them. So 1, 2, 3, 0, -1, 2, 0, 0, 1, 1, 2, 0. We can add them similarly, just the result here would be 1, 0, 3, 0, 5, 2. I just add them component by component. It's called component wise. But if I have a matrix which is 3 by 2, like this one, and I have another matrix which is 2 by 2, like this one, their sum is not defined. So sum is not defined. We can, these numbers, 3 by 2, this is called the dimension of the matrix. We can only have the addition of two matrices if the number of rows are the same, the number of columns are also the same. Okay. And then the definition of this sum is as straightforward as you can see. Okay, so now look at this example where the field, we fix the field to be the set of the field of real numbers, and I define V to be the space of all n by n matrices over R, where n is just a positive natural number. So all these, so we usually show a general matrix with this notation, say A11 up to A1n, AN1 up to ANN. These are just numbers, right? Where each number here, each number Aij is something in R. That's the notation to show the set of matrices, n by n matrices, where each element comes from real numbers. Now, first of all, is this a space? Is V a vector space over R? Okay, it's a question. So we should check to see if the definition of a vector space over a field, which here is R, if it applies here, if it holds. Think about this one for a few minutes, and then I would write down the answer. Okay, before continuing, is there any question?
I was confused about whether or not we were just looking at the addition properties or both matrix multiplication too.
Mm-hmm. Yeah, so here we want to see if V is a vector space over a field. And for vector spaces, we only define addition. So here when I say is V a vector space over R, by that I mean V with this addition of matrices, which I defined here. Is this pair a vector space over R? There is no, at this point, there is no multiplication. We necessarily don't have multiplication of two vectors. We only want their sum. Okay, does anyone want to give an answer? Positive or negative?
I think it is.
It is. Okay.
I think it is, but I am absolutely clueless how you would go about trying to prove this.
Okay. Okay, so let me write down the proof then. So let's go back to the definition of a vector space. The first part of the definition was associativity of addition. What does that mean? It means if I take three matrices, let's show them with A, B, and C. These are three matrices, say n by n matrices. Actually, it doesn't need to even be n by n. It can be n by m. Doesn't really matter. Let's take three matrices. We defined the definition of sum of two matrices. So we can look at A plus B, then plus C. Also, we can look at B plus C, and then A plus that. And I should show these two quantities, these two matrices are equal. That's the first part of the proof. How would I go around doing that? So the point is that any matrix A, which is an n by n matrices, is a table of some real numbers. Okay, I can write down and list those real numbers. So the first one here, it has n columns, n rows. So I would write down A11 for the first number in the first row, A12, etc. The last number in the first row, I would show it with A1n, okay? Now I would go to the second row. I would show the first number there with A21. So the first number here 2, here 1, the first one shows the number of the row. And the second number shows the number of the column. So the second element in this row would be A22 up to A2n. And then it continues. The last row, the numbers, they would be AN1. It's the nth row, first column. The next number would be AN2. It's the nth row, second column. And the last number there would be the nth row, nth column. So I should show it with ANN. And these numbers Aij, where I and j are just two, so these numbers A with two indices, I and j. These I and j are just natural numbers between 1 and n. These are all real numbers. B, in a similar way, is again a table of numbers, real numbers. This time I would show the elements here, B11, B12 up to B1n, and completely in a similar way, Bn1, Bn2, Bn. And C again is another matrix of real numbers. I show the elements with C11 to C1n, Cn1 to Cn. Okay. Is there any question about these notations we're using, this way of presenting the matrices? Okay. So now, rather than writing this equation in this format, I would use this table of numbers I have. So, okay, okay, so I want to show A plus B plus C is equal to A plus B plus C if I change the places of parentheses. So now let me substitute A by what table it really is. So rather than writing A, I would write down A11 up to A1n and AN1 up to ANN. And then I want to add it to B11 up to B1n, Bn1 up to Bnn. I close the parentheses and then I would add it to C11 up to C1n, and then Cn1 up to Cnn. Okay. Now, just by the definition we had for matrices, the sum of two matrices is going to be component-wise sum. So if I compute the sum of these two matrices here, the first element in the first row would be A11 plus B11. So first we would add the first element in the first row to the first element in the first row of the second matrix. What would be the second element in the first row? Well, here, the second thing, which I didn't write it here, would be A1, 2. Here, the second thing would be B1, 2. So the second element in the first row would be A1, 2 plus B1, 2. And the same thing continues until the last one, which is A1n plus B1n. We should do that for each row. What is the last row? It's an1 plus bn1, an2 plus bn2, up to ann plus bnn. That's the result of the sum of first two matrices. So just in order to understand what's going on, I would put parentheses around these things. I would tell you why I'm doing that. It's just to clarify what property we are going to use. And then we still have this matrix C, C11 up to C1n, Cn1 up to Cnn. Okay. So the result would be, okay, I would rewrite that here. We had A11 plus B11, A1n plus B1n, an1 plus bn1, ann plus bnn, and then I have C, C11 up to C1n, Cn1 up to Cnn. Okay, what is the sum? Again, we know the sum of two matrices is defined component-wise, so I should add the first element in the first row to the first element in the first row of C. So I would get A11 plus B11, which is the first element in the first row of the first matrix, plus the corresponding element in the second matrix, which is just C11. And I should do the same thing for the other components. The last element in the first row of the first matrix is A1n plus B1n here, and then we would add the same corresponding element in the matrix C, it's C1n. We continue doing that for all components. Okay, what we get is a matrix. What is this matrix? This matrix is A plus B, parentheses, it means first add A and B, and then plus C. This is the result. Now, look at each component. For example, let's look at the first component here. The numbers in this component, A11, B11, C11, they are real numbers. They're just 1, 2, 3, minus 1, square root of 2. They're just real numbers, numbers we work with every day. We know in addition of real numbers, the order doesn't matter. It doesn't matter if you first add A11 to B11 and then add C11, or if you first add B11 to C11 and then A1. Right? For real numbers, it doesn't matter. We know for 3 real numbers, we can add them in any order we want. Have that in mind. So this is A plus B and then plus C. Let's keep it here. Is there any question for this addition here? How we got here? Okay. If not, let's go to the other side of the equation. Remember, our goal is to prove A plus B and then plus C is equal to A plus, well, first add B and C and then add A. On one side, we computed what is this thing, A plus B and then plus C. That was the matrix we just had. Now let's do it for this other side of the equation. Let's compute the right-hand side of the equation. So again, for A, I would write down the exact table of numbers which A represents. A11 up to A1n, AN1 up to ANN plus. Parentheses, B11 to B1n, PN1 to BNN. And then I have C11 to C1n. The last row is gonna be CN1 to CNN. Now here, first I should compute the sum of these two matrices. So if I do that, again, I should look at the first element in the first row and the corresponding element in the second matrix. The sum would be B11 plus C11. I get that. I should continue that. I would get B1n plus C1n, then BN1 plus CN1 up to BNN plus CNN. I add all the elements in the matrix B to an element in the matrix C, which is in the same position, right? And then I should add the result to A11 to A1n, AN1 to ANN. I should add that to this matrix, okay? Okay, the result would be, well, what was the matrix we wanted to compute? It was A11 to A1n up to ANN. We wanted to add that to this matrix we had, B11 plus C11 up to B1n, C1n, BN1 plus CN1, BNN plus CNN. Now, again, using the definition of sum of matrices, I should add the first element here to the first element here. It would be A11 plus B11 plus C11. But note that we have parentheses here, which means first add these two and then add A11. Same thing holds for the other components. I would just write down the other components of this matrix. Now, what we have here is A plus B plus C, where first we compute B plus C and then we add A, okay? What do we want to prove? We want to prove A plus B then plus C, and if, on the other hand, if we compute B plus A plus B and then add C, or if we compute B plus C and then add A, the results are the same. The right-hand side of that equation is this matrix, right? The other side of this equation is this matrix. As you can see, the components are very similar. There is a small difference in them. On one side, we have A11 plus B11 plus C11, etc. I wouldn't write all the elements. I would just write two of them. On one matrix, we have this thing. And on the other matrix, we have these elements. Now, the question is that, are these two matrices equal or not? Are these two matrices equal or not? The answer is yes. Why? Because these two elements are equal. These two elements are equal. And in a similar way, every other two corresponding elements are equal, because these are just real numbers. And for real numbers, we have the associativity. We know for real numbers, this property holds. And because every two corresponding elements are equal, two matrices are equal. That's just the definition of equality. If you have two matrices, if you look at the components at the same position in both of them, if all of them are equal to the corresponding element in the other one, here the red one is equal to red one, blue one equals to blue one, and the same thing holds for all other elements which I didn't write, then two matrices are equal. So the result is A plus B plus C is equal to A plus B plus C. That's just the first step in the definition of a vector space. All other parts, they can be proven completely similarly. For example, the second part is A plus B is equal to B plus A. I would write it down faster. Just before continuing, is there any question from the previous part, the first part of the proof? Is it clear for everyone? Okay, no question? Good.
Yeah, pretty clear.
Okay, that's great. So I would be a little faster. So here, if I use A and B and use the same notation as before, A plus B would be A11 plus B11 up to A1n plus B1n, and AN1 plus BN1 up to ANN plus BN. That would be A plus B. What is B plus A? It would be B11 plus A11. The order has changed. First B and then A. Up to B1n plus A1n. What is the last row? AN1 plus BN1 up to BNN plus AN. In order to show these two are equal, I should prove these two matrices, these two table of numbers are equal. I should show the blue equality. Is that true? Is that correct? Yes, it is. Why? Because A11 plus B11 is equal to B11 plus A11. Why? Because A11 and B11, these two numbers, they are real numbers. Real numbers commute. 2 plus 3 is equal to 3 plus 2. We have this property for any field, including the real numbers. A1n plus B1n is equal to B1n plus A1n. The same thing holds for any two component and the corresponding component in the other matrix. So all components are equal to their corresponding components in the other matrix. So these two matrices are equal. So it has the second part of the definition of a vector space. That's good. What was the third definition of a vector space? It should have zero vector. Here we should have zero matrix. What is zero matrix? It's a matrix which, if I add it to any other matrix, it wouldn't change that matrix. A plus 0 or 0 plus A is just A. Well, can you guess what matrix is that?
Just a matrix of zeros.
Yeah, all over the place, right? All of the elements are zeros. So if you add this matrix to any matrix A, you would get 0, 0, 0, 0, plus the matrix A, which is A11 up to A1n, AN1 to the ANN. Each component would be 0 plus A11 up to 0 plus A1n, 0 plus AN1, 0 plus AN. So again, this 0 here and here and here and here is a 0 as a matrix. The zeros here in the components are zeros as a real number, just 0, 0, 1, 2, 3, right? So I know 0 as a number plus A11 is just A11. I know the number 0 is identity element of addition. 0 plus A1n is just A1n. This is just AN1. This is just ANN. So this thing is equal to A11 up to A1n, AN1 up to ANN. And this is just a matrix A. So I started with this matrix 0 plus A. I ended up here at just the matrix A. So 0 plus A is just A. A plus 0, similarly, is just A. So we have the identity element. I'm not sure if we use 0 as a matrix. What is the good notation for that? Yeah, I'm not sure. Maybe at some point we can think about a good notation for 0 as a matrix in order to not to confuse it with 0 as a number. I don't think there would be any explicit element.
Maybe you could like bold it.
Like what?
Bold face it. I think.
Well,
that's
yeah, maybe. maybe we can use it a little bit bigger, something like this. It's a little bold and bigger. Yeah. So 1 is 0 as a matrix, 1 is 0 as a number. I have 1 more minute. So in this 1 more minute, let's get to the next property of a vector space. So probably, as you guessed by now, it is really a vector space. The set of n by n matrices over R is a vector space. I would get to show you that we have the 4th property, the inverse for inverse elements for of addition. So we have A. We should say there exists another matrix, which if we add that matrix to A, we would get 0. Actually, we show that other matrix with minus A, which is easy to guess. If the matrix A as a table of numbers is just A11 up to A1n and AN1 up to ANN, this matrix minus A has all elements multiplied by inverse. So it's just minus A11 up to minus A1n minus AN1 minus AN. So if we add these two matrices, every component cancels the corresponding component. So for example, if, just as an example, so if one matrix, say we have a 2 by 2 matrix, 2, 3, 4, minus 1, minus A is just minus 2, minus 3, minus 4, and 1. And if we add these two matrices, we should add 2 with minus 2, we get 0. 3 with minus 3, we get 0. 4 with minus 4, we get 0. Minus 1 with 1, we would get 0. So that's how it works. There are 4 other properties you should check. You can check them all. They're all as easy as what I did here. There is no surprise there. Okay, is there any question here? Maybe I think I have time for one. Oh, I'm over time actually. I didn't know that. I'm sorry. I thought we have time until 12:45. Actually, we have time up to 12:40. I'm sorry. Is there any question here? Okay. Okay, that's great. I guess I'm over time. So let's continue next week. You can also come to my office hours and MLC hours and ask me any question you have. Okay, bye.